So let's start our learning of Newton's 3 laws in action with law number 1, part number 1, objects at rest stay at rest unless acted upon by an unbalanced force. So rest in this case means an object that is not moving, it's not going anywhere. And to understand what unbalanced force is, we got to understand what balanced forces are. So we have a ball that's just hanging out on the ground. Gravity is pulling down on the ball and the ground is pushing up on the ball with what we call a normal force. All the forces acting on the ball, the object, are equally opposed to each other. And so the ball isn't going anywhere because everything is just equal and balanced out. Free body diagrams help us to understand what's happening to objects because they show the forces that are acting on those objects. The longer the arrow means that the bigger the force, sometimes they're also fatter as well. And the direction of the arrow tells us, guess what? The direction of the force. So here we can see a ball, it's just hanging out. Gravity's pulling down, ground's pushing up, not going anywhere. So an unbalanced force happens when one or more forces are larger than the things that would otherwise balance them. Like when you kick a ball, you apply a force to the ball that is not balanced by a force that's equal in opposite direction. So you can see we kick the ball, and because it's an unbalanced force, the object accelerates or changes its motion. This acceleration always happens in the direction of the unbalanced force. So when objects are sitting still, they don't just start moving because it takes an unbalanced force to make that happen, which is good news for dogs and babies and cactuses. But if we apply an unbalanced force, boom, then the object accelerates. So part 2 of Newton's first law is that objects in motion remain in motion at the same velocity unless acted upon by an unbalanced force. Now this one's really tricky and it's kind of hard to prove on Earth because we always have gravity and friction messing with the motion of objects. So things here don't just stay moving. So let's say that you're driving down the street. Gravity is pulling the car down, normal force is pushing the car up, right? So we're not plummeting to the center of the earth or floating up into the sky. The force of the engine is balanced by the friction on the road. And so if you're driving a car in a straight line, you maintain a constant velocity, like when you have on cruise control. There's no need for any extra force to change your motion. You just keep a constant amount of force to keep you moving down the road. But if you want to accelerate that car, if you want to speed up, slow down, or turn the car, you have to add an unbalanced force. So again, gravity and normal force are still acting, but if you wanted to speed up the car and you apply an extra force to the engine that is not balanced by friction, then you're going to accelerate. Same thing as a ball falling down a slide. If you wanted to slow down the car, you would have to change the applied force, right? So that the force of the engine is less than the force of friction. And you do that by either applying brakes or just taking your foot off the engine and allowing friction to be a greater unbalanced force to slow you down. So there's a couple ways on Earth to slow motion because friction will do a lot of that work for us. Kind of helpful. So right, if Bo wants to stop running, he has to slow down. And the same thing with his bat or this bowling ball. Friction will just slow it down. Now, if we want to turn, we do have to apply an unbalanced force, right? In the opposite direction of where we want to turn. So we would turn a steering wheel in a different direction, or if you wanted to turn on a swing, then the tension force on the rope applies a force to make the boys turn on this swing. So things don't just move on their own. If we want them to speed up, slow down, or turn, we're going to have to apply a force to make that happen.